This is a video on sound, hearing and ultrasound, and the ultrasound section is a separate video actually, but I wanted to start off with looking at what kind of wave sound is, and then looking at how the properties of the wave and the properties of the sound are connected, then look at how we hear things, and finally I'll refer you to my other video on ultrasound. Whilst we're going through here, you should be making notes, filling in the answers to the questions on the template that I have shared with you. So let's first of all remind ourselves what kind of wave sound is. So here you have the oscillations on the left-hand side, the hand. Let me just take that back a little. The hand is moving from left to right, and you see the energy being transferred through the medium, in this case the slinky, from left to right. So this is a longitudinal wave. I'll go back a little bit further there now to show you. There's the compression, the high pressure area. And here you have the rarefaction, the low pressure area. You can see the coils, the particles of the medium in this case are pulled further apart. So this is a low pressure area. It's called a rarefaction. And the high pressure area where the particles are squeezed closer together, that's your compression. So sound is a longitudinal wave. How then are the properties of the wave and the sound we hear connected? So you can see as the pitch of the note increases, watch what happens on the oscilloscope. You can see that the frequency of the wave is increasing. Now, this looks like a transverse wave. It isn't. What's happening is that this machine, the oscilloscope, what it does is to cause a bright spot to move across the screen. And what this does, the signal generator, it makes the spot move up and down at the frequency that's set on here. So as the spot moves up and down, it moves across the screen and you get this nice wave pattern. So it isn't a transverse wave, but it allows us to see how, as we change the frequency, how we change the amplitude, as we will do later, how that affects the frequency and the amplitude of the wave. So as we change the loudness of the sound and the pitch of the sound, we change the amplitude and the wavelength of the wave. So there we have changed the amplitude of the wave. You see the wave getting bigger and smaller, the amplitude being the maximum displacement from the rest position of the particle of the medium. You can see that as the sound gets louder, the amplitude of the wave causing the sound gets bigger. Now that distinction is important. The amplitude and the wavelength or the frequency, these are wave properties. The loudness and the pitch, these are sound properties. So if you're talking about sound, talk about the loudness, talk about the pitch. If you're talking about the wave causing the sound, talk about the amplitude talk about the wavelength or the frequency and pitch being the two that are connected. So there we're increasing the pitch, decreasing the loudness, increasing the loudness, increasing the pitch, and you can see throughout all of that the effect it's having on the wave causing the sound. So we've looked at what kind of wave sound is. It's a longitudinal wave. We've looked at how the properties of the wave and the sound are linked. The next thing to look at is how we hear things. So we know that sound waves are longitudinal waves. So these compressions and rarefactions are arriving at the outer ear here, the pinna, this is called, the flap of skin on the side of your head. Those sound waves then travel down the ear canal, and the ear lobe, the pinna, earlobe it's called here, but it's really called the pinna. The pinna and the ear canal, these make up the outer ear. Then here we have the eardrum. So the sound wave comes in, the compression hits the eardrum and it moves in. The rarefaction hits the eardrum and it moves out. So the eardrum vibrates. That vibration then gets amplified by a series of three bones. Hammer, anvil and stirrup, we often call them. Their names here properly malleus, incus and stapes, but hammer, anvil and stirrup they're called. And what they do is to amplify that relatively small motion to make it a bit bigger over here. So the stirrup is attached to the oval window of the cochlea. And in the cochlea, you have fluid. So as the stirrup moves in and out, the fluid in the cochlea moves backwards and forwards. All around the walls of the cochlea are little hairs. Hairs of different lengths that will respond to different frequencies of sound. So as the hairs move, they're attached to nerves which send signals to the brain. So that's really how you hear. The semicircular canals here in the inner ear, along with the cochlea, the semicircular canals have got nothing to do with hearing. They're about balance. There's fluid in these semicircular canals, and the movement of these fluids tell the brain which way up you are. It tells the brain what to do. If you want to stand up, then it detects that and it sends signals to your legs to get them to straighten. But if this isn't working properly, then you may not be able to stand up. You may feel dizzy and nauseous because you're getting confused signals to your brain. So an infection of the inner ear can be quite serious, quite debilitating. But back to the hearing. So this eardrum responds to sounds from 20 hertz to 20 kilohertz, 20,000 hertz. That's very impressive. But in order for it to do that, it has to be very thin, very low mass, which means it's really easy to damage. So sticking a cotton bud in here, or a loud sound, a really big amplitude, or even a relatively small amplitude, but close by so it doesn't have time to lose energy before it gets to your ear. This can cause damage to the eardrum. It can also cause damage to the hairs in the cochlea so that they lie down and are no longer responsive to the sound, the movement of the fluid, or they break maybe. So if you're near an explosion, for example, the explosion could tear your eardrum. A blow to the head could dislodge these three bones, so they're not connected anymore, and so the vibration doesn't get passed on. Loud sounds, explosions, could break or damage the hairs, make them lie down in here. So your eardrum, it will heal if it gets torn, but with any flesh that gets damaged, there will be scar tissue, and that will make it less responsive. So these are the reasons why loud sounds, cotton buds, blows to the head. You know, if someone was to slap you on the ear, that pressure wave could tear your eardrum. It could make hairs in here lie down. On a separate point, you'll be aware that you sound different to yourself to the way you sound to other people. And that's because what you hear is a combination of what comes in through your ears and conductive hearing around your skull. So we hear ourselves as a combination of the two of those, whereas everybody else just hears what we would hear through our ears. So we sound different to other people, to the way we sound to ourselves. It also means that even if your ear isn't working, even if you lost your eardrum, you will still hear something because you will still have that conductive hearing. Profound deafness is where neither of those work. So you have what is a sound wave. It's a longitudinal wave. And we've talked again about the compressions and rarefactions, high pressure, low pressure areas. We've looked at the connection between the properties of the wave, the amplitude and the frequency, and the properties of the sound, the loudness and the pitch. We've looked at how the ear actually works, and we've looked at some of the issues we can have with the ear. So, that's the end of this video. You should look at ultrasound. One thing I didn't mention here, we've also covered the range of hearing, 20 hertz to 20 kilohertz. As you get older, that 20,000 hertz comes down a bit, so my hearing range would be slightly less than yours probably.